Okay, I think we get started. We have a quorum. This week, we're very happy to have our very own Stan Trier. Stan got his MS degree in meteorology from Penn State in 1987, prior to joining NCAR in 1988. While working as an associate scientist in M-Cube, he completed his PhD in atmospheric science at CSU in 1997, and he became a project scientist in MMM shortly thereafter. Stan is well known for his studies of deep convection and its mesoscale environment, using both simulations and observations, along with keen physical insight to decipher the complexities of these systems. Stan is active in the meteorological research community, serving on AMS science committees and organizing national conferences. In 2019, he received the AMS Editor's Award for Monthly Weather Review, and since then he's been an editor at Monthly Weather Review. So today's talk is the mesoscale environmental conditions accompanying tornadoes in eastern U.S. landfalling tropical cyclones. Stan?
All right. Thanks, Rich. I was trying to decide whether to do a dynamics happy hour or an M-Cube seminar, and part of that was Rich was getting on me to do an M-Cube seminar, but then the actual reason is I'm too cheap to buy the beer and all the refreshments. Anyway, this is work that uses composites to emphasizing the spatial structure of environmental conditions associated with tropical cyclone tornadoes. It's funded by NOAA as part of the Vortex Southeast experiment and in the NCAR STEP program. It's been a real team effort, this project. I've had a lot of assistance from others. I'd like to give special recognition to Dave Ahievich, who created the machinery to do the composites for this study, which are the centerpiece of this study. Also, Derica Carroll, who's a visitor at NCAR, made a huge contribution going through a lot of different cases and categorizing them in different types of tropical cyclone tornado environments from which these cases were used to create the composites. Also along the way, I've gotten a lot of advice from George and also our NOAA collaborator, Roger Edwards, who's a lead forecaster at Storm Prediction Center, and he's actually recognized as a real pioneer in research of tropical cyclone tornadoes. And also like to acknowledge Chris Davis, who gave me a lot of ideas for this project and encouraged me to kind of get involved in this arena. And 5 years later, I actually have something to show for it. And then also Morris, who's done a lot of work in this area with Bill McCall, dating back to the Clem Wilhelmsen model simulations of tropical cyclone thunderstorms. And also Ben Schenkel from the University of Oklahoma, who's worked in this area more recently. So I'd like to start off with an example of a landfalling tropical cyclone that produced tornadoes. This was Hurricane Lily, which was a moderate strength or a Cat 1 hurricane that came on shore in the Gulf of Mexico. And it has kind of an interesting relationship with the track with tornadoes, because there's one cluster that's kind of located near the center of the storm as it's making landfall. But also there are these tornadoes that are located quite a bit east of the center in southern Louisiana and Mississippi later in the day, and these are occurring within the outer rain bands of the tropical cyclone, and that's where most commonly these tornadoes occur. And you can see they're associated with the environmental field of fairly strong 0 to 3 kilometer storm relative helicity. Tropical cyclone tornadoes, which I will abbreviate as TCTs throughout this talk, are just one hazard that are associated with landfalling tropical cyclones, which I call LTCs. They only account for about 3% of the fatalities, but their precise locations are more difficult to predict than from these more widespread type of hazards that people are usually more keyed in to with tropical cyclone landfalls. And Another issue is the awareness of the public of these tropical cyclone tornadoes, because I was just talking to Chris the other day, and he mentioned this, and it's a really good point, that they tend to occur quite far away from the areas where there's widespread wind damage. So people often think, well, the track is several hundred kilometers, predicted to be several hundred kilometers away. Do I need to worry about tropical cyclone tornadoes? And the answer is sometimes yes. There are some generic ingredients for tornadoes related to the mesoscale environment, and this includes non-tropical cyclone tornadoes, and they require some buoyancy in the sounding, which is usually measured by the Cape. It turns out that in tropical cyclone tornadoes, you don't usually have nearly as much of that as you have in central US continental tornadoes. But what's almost universal is you've got large vertical shear in the environment of these tropical cyclone tornadoes. And I want to point out this paper by Roger Edwards, our NOAA collaborator. This is probably the most extensive review of tropical cyclone tornadoes, so I encourage anyone who wants to know more about the subject to read this paper. Okay, the primary focus in this talk is using the reanalysis composites to determine spatial structure and the diurnal cycle of the tropical cyclone tornado predictors for the different TCT environments. And we compare these composites to TCT frequency analyses, which hopefully can, with the goal of increasing situational awareness for forecasters when they write their mesoscale discussions and watches. It's sort of at those timescales that we're trying to improve the forecasts. It's well known that the strongest landfalling tropical cyclones produce the biggest tropical cyclone tornado threat, but I think one of the outstanding questions is really for these weaker landfalling tropical cyclones, what determines whether it's going to cause a big tornado outbreak or be kind of a null case, because it can really vary quite a bit. The second question, in the last few decades, there's been a lot of development in the forecast community of these composite severe weather predictors. And one of the things that we looked into in this study is, do you get much improvement looking at these composite predictors that depend on a couple of different meteorological parameters than just looking at individual single meteorological fields? So that's something we've addressed. And most tropical cyclone tornadoes occur within 100 kilometers or so, a few hundred kilometers or so of the coast, but some occur well inland in several diurnal cycles after the landfall. So we also investigated what might be unique about that environment. The talk follows this outline. It's based on a paper that's just been accepted in the last few weeks and is currently in AMS early online release. It's in WAF. This is a brief outline. We'll talk about some of the technical issues involved in making these composites at the beginning of the talk. And then items 2 through 4 are really the scientific content. We're interested in looking at the diurnal cycle of these tropical cyclone tornado environments, and the mesoscale conditions in contrasting environments, ones that produce many tornadoes versus other environments that don't produce as many tornadoes. And finally, we'll look at a comparison between these inland tropical cyclone tornado environments with the more generic tropical cyclone tornado environments. So these are the different environment types for the composites. The different categories in the rectangles are based on the tornado frequency within the landfalling tropical cyclones. These are categories 1 through 4. They're mutually exclusive. There is a generic category that we've constructed based on averaging all the cases in these first 4 categories, which we call the all cases category. And then finally, we have the inland category, which has cases drawn from composite environment types 1 and 2, but later in the life cycle of the landfalling tropical cyclone, maybe 2 or 3 diurnal cycles after it's made landfall. And I should mention that in categories 1 through 2, which have many tornadoes, that's greater than 10 tornadoes, greater than or equal to 10 tornadoes. We've got one category in which we have very strong landfalling tropical cyclones, category 2 hurricanes or greater, and one's number 2 with weaker landfalling tropical cyclones, cat 1 hurricanes or tropical storms. Okay, so based on what our objectives in this study are, to look at the diurnal cycle and also look at, what's different in the environment between these different classification types, this necessitated us to make some choices in what cases to put in the composites. You want to be able to really sample all around the storm as it comes in. And Dave created these nice plots showing the tracks, and I'm showing the example for the strong landfalling tropical cyclone, mini tropical cyclone, tornado environment type. And where the storm tracks become solid is the 24-hour diurnal cycle portion of the track that we're using in the composite. And it's color-coded. The tornadoes symbols that are plotted on there are color-coded to match the storms that they come from. This is the panel on the left. Now, we did have to exclude cases based on sampling issues, and they're in the rectangle down at the bottom of the slide, these different types of cases. And I'll just go through them really briefly. LTCs with northeastward moving storm tracks near the immediate or southeastern US or mid-Atlantic coast, like these guys right here, there's a whole side of the storm, and this is the side where the tornadoes most frequently occur, that's over the ocean, and you can't sample them. So if we threw these in, it would bias the composites. So we eliminated those cases. As I mentioned, we're also interested in looking at the diurnal cycle. So these cases that moved really rapidly across the Florida Peninsula, that were over land for less than 12 hours, we threw those cases out as well. There are also cases that make landfall, for example, in Mexico, but produce some tornadoes over the United States. A large portion of these storms don't have data, don't have soundings, or don't have tornado reports. And then there was another type of storm that we excluded that's not in this particular composite, but there were storms that were in the Gulf of Mexico that had really large circulations that would produce tornadoes near the coast, but produce the majority of their tornadoes while the storm was still over the ocean. And in those cases, you wouldn't be able to sample the whole storm. So we ended up throwing out about a total of a third of the actual cases in this 27-year data record. And we made the data record 1995 to 2021 to match that of the tropical cyclone tornado database that's compiled by Roger Edwards. Okay, so this slide shows how we composited these NCAR reanalysis. We composited them relative to the tropical cyclone tornado center, which was determined from the IBTRAX data in 3 different coordinate systems that are shown. The first one is the standard fixed Earth coordinate system, which really needs no explanation. This one in the center is a coordinate system that moves with the tropical cyclone. It's a tropical cyclone heading relative coordinate, where the direction in which the tropical cyclone is moving is at 360 degrees here, called the front. And this is often used in the hurricane community. The tornadoes often occur in the right front quadrant, sometimes in the right rear quadrant. And then we had a coordinate system that's aligned along the deep shear through the depth of the hurricane, and this is a shear relative coordinate, and we followed the methodology that Chris used in a 2008 paper to determine this environmental shear. And here it looks quite different, the example predictor field and the tornado, tropical cyclone tornado frequency, which I have in the thin contours, which has units of inverse time and inverse area. It just shows the density of tornadoes. It looks very different in this coordinate system. The ground relative coordinate system and the TC relative coordinate system actually look fairly similar to each other. And the reason for this is most of these storms had a dominant northward motion. But in some of these categories with fewer members, you can see differences, but they're really not that great in these, in between these two coordinates. Now I want to say something about this tropical cyclone tornado frequency field, which I have in contours. It's based on work that Bill McCall did in the early 90s, and it's called the F-sum. And the F-sum is it counts each tornado, it weights them based on their strength. So an EF0 tornado would have an F-sum of 1. An EF2 tornado would have an F-sum of 3, for instance. So you don't have, in tropical cyclones, you don't tend to have tornadoes that are much stronger than, very frequently have EF2s. That's about as strong as they get. So it's slightly weighted toward the stronger tornadoes, but it's really a tornado frequency diagram. And I want to point out that this scale is a multiplicative scale. So each contour has twice the frequency as the contour beneath it. And it was necessary to make the contours this way because we had large variation among the categories and we wanted to compare each other. So that's just something to keep in mind. Now, because we relied exclusively on the NAR reanalyses to make the composites, we had to establish that the NAR analyses had good fidelity. So we compared them with co-located National Weather Service soundings. And I have a couple of plots of that on this slide right here. On the top, I have moisture variables, and you can see that they're very well correlated. And there are also large regional differences depending on what side of the storm you're on. The blue symbols are on the left side of the storm relative to the tropical cyclone heading. And that is, and the red symbols are on the right side of the storm, and about 80% of the time that's the down shear direction. So you can see that they're very well separated from each other, and the average difference between these different regions in the storm is much greater than the biases or even the typical scatter that you see. So that means that the patterns are going to be very faithfully reproduced by the NAR. It's a little bit of a different story with some of these wind shear variables. The bulk wind difference is sort of an approximation of the wind shear through certain depths. And you can see for the low level shear, there's definitely a bias. The shear values are too weak in the NAR. That could possibly be due to its limited vertical resolution. It has grid spacings of 25 and 50 millibars. So that could be one of the issues. Also, when you get really close to the center of these storms, the winds are very strong. And if you're comparing them to soundings, the soundings are going to have some drift. So you're actually, with the soundings, you're really not exactly looking at the wind shear. So we tried to mitigate this by only doing the comparisons with soundings that were more than 75 kilometers away from the center, but we also wanted to be within the TC circulation, so we didn't have anything farther than 750 kilometers. This issue with the strength of the NAR vertical shear is less of an issue as you look at shear through deeper layers. There's really not much of a bias when you look at the shear from the surface up to 5 kilometers or so. So this is the, for the too many tornado categories. These box plots show the frequency of the tropical cyclone tornadoes within these two different categories. And what really jumps out, if you look at the center box plot and the right box plot on each panels, is there's a very strong diurnal cycle. They're much more common during the day, these tropical cyclone tornadoes, also, there's a fair range within the categories. I mean, you've got some systems that produce a ton of tornadoes, but all of these cases produce at least 10 tornadoes during their lifetime. Now, this plot just shows the number of tornadoes during the different during the actual diurnal cycles we used in the compositing. So the actual total amounts are about double, because some of these cases produce tornadoes over two to 3 days after they made landfall. And on these plots, we don't have a lot of cases in each category. For the strong LTCs, we have 16. The weak LTCs, we have 23. So the whiskers actually represent the extremes, not the 90th percentile, which you sometimes see, but the boxes are the 25th to 75th percentile. So you can see there's a fair range and a strong diurnal cycle in the number of TCTs. So this plot shows the diurnal cycle for the 72 case generic composite, which we call all cases. The color shaded fields on here are the 10 meter to 700 millibar bulk wind difference magnitudes, and the bold contours are the mixed layer CAPE with contours of 250, 500, 100, and 1500 joules per kilogram. The thin contours are the TCT frequency, which is maximized in the northeast quadrant, very close to where the bulk wind difference is maximized. And you can see that there's a strong diurnal variation here. They're they're about 4 times as many tornadoes in the afternoon as there are overnight. In the next slide, we're going to compare a time series from near the average position of the TCT maximum in these plots, which is denoted by the blue cross symbols. And we're also going to compare it to a corresponding position shifted 180 degrees on the opposite side of the TCT, which is denoted in orange. And here are the time series for the different fields. And if you look at the mixed layer CAPE, the values, compared to continental tornado environments are pretty small in these average cases, and they were maximized in the morning and the afternoon, on average, about 550 joules per kilogram. The color shadings actually represent the 95th and the 5th percentiles here, determined from bootstrapping. But even with the small CAPE, there's a very significant diurnal cycle. You can see it reduced to about an average of 300 joules per kilogram overnight. And at all times, it's significantly less on the left side of the storm, which is the upshear location. You can see even bigger differences during the diurnal cycle in the low-level vertical shear and in the relative humidity in the middle troposphere. A little bit less of a difference in the mixed layer SIN. Actually, at the time of maximum tornadoes in the afternoon, there's not a statistically significant difference. And the reason is that on the east side of the storm, where the tropical cyclone tornado maximum is, it's moister, but it's also cooler. It's warmer and drier on the other side, and so these effects sort of cancel each other a little bit in the SIN. It should show some soundings from the two different areas. On the left panel is the tornado proximity sounding. This is an average of 72 cases, so it looks pretty smooth, but you can see this deep layer of near saturation with moderate values of CAPE and a very favorable curvature in the hodograph to support rotating storms. Much drier on the other side of the storm with less cape. Okay, so now I would like to look at the effects to show how more favorable conditions develop after the tropical cyclone or after LTC landfall. And in this plot, I'm using the strong LTC many TCTs environment type as an example. The color shading on these left-hand panels is the 10-meter wind. And in the center panels, it's the 700 millibar wind. And you can see a substantial weakening of the surface winds as you would expect after landfall, but there's not a corresponding weakening at 700 millibars, and this leads to very large increases in vertical shear, which you see on these rightmost panels. And the TCT frequency maximum is located right where there's this large increase in vertical shear. If you look at the Cape, which is the bold contours, you can see that it's not really correlated very well at all with where the tornadoes are, but it's actually fairly important, which we'll get to later. So this is a plot from Rosemar's recent review article on hurricane intensity, and it really in a different context from this talk, but I think it's very, it's very useful to explain some of the changes that happen as the storm moves from over the ocean to post-landfall conditions. Storms are often intensifying prior to landfall, and they're characterized by fairly symmetric pattern of convection on both sides. In these plots, the blue arrows show the secondary radial circulation associated with the hurricane. And you can see it really changes in a non-intensifying tropical cyclone that has asymmetric convection biased to one side. The shear is a lot stronger in that case, and you tend to develop more of a vertical motion couplet in that case. So what's actually bad for hurricane intensification, it turns out it's good to support these tropical cyclone tornadoes because they like strong shear, and you have stronger shear in this environment after the landfall. And it's nice to see that this is captured pretty well in the NCAR. This is our 72 case, or actually I'm using the strong LTC many TCTs environment in this case. And you can see prior to landfall, fairly symmetric vertical motion pattern, fairly weak vertical shear. This is the vertical shear through the lowest 3 kilometers. After landfall, you develop this vertical motion couplet. Much stronger shear. It increases the bulk shear through the lowest 3 kilometers, increases from 8 meters a second to 16 meters a second. And you can see that the tropical cyclone tornado frequency maximum is located near where this vertical shear is the strongest. Okay, so now I want to move on to the part of the talk where we talk about tropical TCT environment predictors, and I just want to show the conditions in 3 of our categories prior to landfall. As you might expect, in the storms that make landfall with strong winds, you can see a much greater difference in the near surface wind in this category than in the other 2 categories. These 2 categories have approximately the same strength of the near surface wind just before landfall, but it turns out that this category has a lot more tornadoes. So what that tells us is the strength of the storm at landfall for these weaker storms isn't always correlated with how many tornadoes that you're going to get. So it depends on other meteorological factors, which we're going to look into. So this is the one table I'm going to show you, but this lists some of the predictors. In the highlighted fields, I have these composite parameters, and we've looked at a handful of them. I'm only going to discuss two of them today, the tropical cyclone tornado parameter, which turns out it has very good correlations for all three of these different coordinate systems. And then the supercell composite parameter, which is a more general parameter that's used to forecast severe likelihood of severe convection. And these other parameters, this is the storm relative helicity through the lowest 3 kilometers, the bulk wind difference from the surface to 700 millibars, and the wind speed, their correlations are good. The best correlation was with the tropical cyclone tornado parameter. Wind speeds at different levels, correlations are moderate. They're not quite as good. Notice that the Cape really has no correlation, but it turns out to be very important. It's not spatially co-located with the tornadoes, but you need to have a certain amount of Cape, which is pretty evident from this analysis, as we'll see. We're looking here at 3 different categories: the strong LTC with many TCTs on the left, the weak case that still has many tornadoes in the center, and the null case that's on the right. The top panels with the color shading are the bulk wind difference is indicated by the color shading. The bulk wind difference from about the surface up to 3 kilometers. You can see, it's correlated very well with the shear in these two cases. In the bottom, I'm showing the storm relative helicity through the lowest 3 kilometers, and that's this expression down here. The C is the estimated storm motion, and we estimated it using the bunkers formula. But you can see that even though we have a good spatial correlation, with both of these fields have good spatial correlation with the TCT frequencies. We also see that the Cape is very important. In this case, that has many tornadoes, this composite, the shear values are stronger, but not way stronger than they are in the null case. They're about 4 meters per second through 3 kilometers stronger. But the Cape near this region of the strongest shear is about 500 joules per kilogram greater than it is in this null case. So you really want to look at both the Cape and the shear in these cases. Now, I wanted to move on to the composite parameters. Here I've separated it into different times of the day. This is day and this is night, and we're looking at the supercell composite parameter, which is defined here, and it depends on Cape, the storm relative helicity, the bulk wind difference through a deep layer. We see that there's really only a weak to moderate spatial correlation with this TCT frequency field, which is in the thin contours. However, it's got a couple of really good attributes. It's a really good discriminator between these cases with weak landfalling tropical cyclones that produce many tornadoes and those that don't. So that's one really positive aspect of it. It also has a strong diurnal cycle, which you can tell by comparing the top row with the bottom row. And you can even see at night that there's these secondary maximum tornado frequency that are actually fairly well spatially correlated with these spatial maxima in SCP. Now, comparing that to the tropical cyclone tornado parameter, which in the table had the largest correlation, that's defined here. That has no Cape dependence. That depends on shear through a lower layer, which might be more suitable for tropical cyclone tornadoes, the storm relative helicity, and it also adds a a relative humidity average through a deep layer, which actually I think helps improve it over just looking at the shear, which we saw in the table. It has a very, very strong correlation with the TCT frequencies, but it's a very poor discriminator between these weak LTCs that have many tornadoes and the null cases. It also has a very weak diurnal cycle, which is inconsistent with what we see in the tropical cyclone tornado frequency. So, you know, if I were a developer of algorithms, which I'm not, I would probably take this algorithm and try to add a little bit of CAPE dependence into it, but not as much as for the central US, you know, cases, which I think SCP was developed for. Okay, I want to move on to the last part of the talk, which is looking at any differences that we see in these well inland tropical cyclone tornado environments. And one difference is quite striking just from looking at the tracks, that they have a fairly prominent eastward component. And that's because they're moving to latitudes where the westerlies are a little bit stronger. So there's much more of a steering flow with these systems. Like in the other systems, the tornadoes occur predominantly to the right of the storm track or ahead of the storm track. Yeah, so that's kind of what you can glean from this diagram. The TCT frequency distribution is fairly similar to the other cases that I looked at, the strong LTCs with many tornadoes and the weak LTCs with many tornadoes. There's a strong daytime maximum in the TCT frequency, which is kind of hard to say. And so in this plot, I'm comparing the diurnal average of the surface to 500 millibar bulk wind difference magnitude and wind vectors in the inland LTCs, which are in this left plot with the more generic composite right here. And there are a couple of differences. The magnitude is stronger. The vertical shear on average is about 4 to 5 meters per second stronger from the surface to 500 millibars than it is in the generic composite. And also the orientation of the shear, which is indicated with these arrows near the maximum, has a much more westerly orientation than it does in this case. So it's probably influenced by this stronger mid-level westerly flow. Also, some other aspects of this inland environment, and I was really surprised that it showed up so strongly in this composite, but there's a very strong, very significant baroclinic zone on the east side of the composite, and that's consistent with the stronger westerly shear from thermal wind considerations. It has a very strong vertical motion couplet, very strong ascent on the down shear or eastern side, a weak ascent or weak descent up shear. And the maximum is actually of tornado frequency is in a region of, it's hard to read these labels, but it's between 250 and 500 joules per kilogram of CAPE. So that's really weak CAPE for a tornado maximum. But the relative humidity in mid-levels of the troposphere is very strong in this area. And there's a whole elongated area of elevated relative humidity that's kind of oriented near this frontal zone. So this lifting that's occurring on the east side of the TCT is probably being enhanced by this frontal zone in these inland cases, which is not an attribute that you see so much in these near coastal cases. Okay, to summarize, we've looked at 72 different tornado cases, and they've been categorized based on 27 years of NCAR reanalysis data, and they've been compared with the TCTOR database, and we've overlaid these TCT frequency fields with some possible predictors. We constructed composites for the different environment types. They're based on the TCT strength at landfall, the number of TCTs, and the different distances of the tropical cyclone and the TCTs from the coast. Emphasis has been on the mesoscale spatial patterns of these environmental predictors. The TCTs are maximized during the daytime in the northeast or right front quadrants where the vertical shear is the strongest. Most frequent and strong landfalling tropical cyclones, but among the weaker cases, both stronger shear and larger cape enhance the TCT frequencies. And I've been asked to sort of give a threshold when I've talked about this before of how much cape is actually needed. And I think that's kind of a tough question, and I think it depends a lot on the strength of the vertical shear and on the mid-tropospheric relative humidity above the boundary layer. In cases where the shear is very strong and it's very moist above, you probably need as little as 100 joules per kilogram. But in these drier cases, like I neglected to mention that the TCT maximum frequency has an elongated lobe here into drier conditions with less shear. And in these regions, it probably requires a lot more cape to get the tornadoes, maybe more like 1,000 joules per kilogram. So that's sort of my answer to that question. And it's a hard thing to put in a formula if you're trying to, develop a predictor. The composite predictors that we looked at, in particular, supercell composite parameter and the tropical cyclone tornado parameter, they definitely add information, but no single predictor simultaneously correlates well with the TCT frequency and also discriminates well between these different TCT environment types. And they don't, some capture the diurnal cycle much better than others. SCP, which doesn't have the greatest spatial correlation with where the tornadoes are, actually gets these other two aspects better than a lot of the parameters. So it pays to look at a lot of different things. That's the message, and it's not very profound. But the well-inland environments are different. They have stronger westerly shear. The mesoscale ascent on the east side, I think, helps enhance the relative humidity above the boundary layer, and it favors TCTs in this environment where the cape's actually pretty modest, often less than 500 joules per kilogram. And with that, I'll stop and take any questions.
Okay, we have time for questions, comments.
Dan, I wonder, you've probably looked at a bunch of radar images or animations associated with these. So do you have a feeling for how the storm structure changes between the near landfall cases and the cases that are much farther inland, especially in the stronger, more frequent T occurrence?
Yeah, I have not looked at that systematically. I had a few examples in here. We've done modeling of these different, taking example cases from this different environment. And this is tropical cyclone Bill 3 days after landfall. And you can see there are lots of spiral bands. It looks a lot like some of these systems that are coming on shore. So I can't, to answer your question, I haven't noticed anything systematically. I did look at a lot of these radar loops to try to determine which soundings to use to do, the NAR comparison. So, that doesn't mean that there aren't systematic differences. I just I'm not aware of them. That's a good thing to look at.
Yeah, in terms of the average tornado that comes ashore, you just know a hurricane comes ashore, you just know there's one coming. What are the chances that a tornado will occur? And how significant is the damage that you expect to see from this type of phenomenon?
Well, the chances that one would occur within the entire life cycle that the storm can still be classified as a tropical disturbance, like greater than tropical depression winds, which I think are, I don't know what, is that 35 knots? I don't know exactly what that threshold is. I'd say that's about 95% that there'll be at least one tornado. Now, the tornadoes don't tend to be nearly as strong as Oklahoma tornadoes, but they affect a part of the United States where there are infrastructure issues. There are a lot of, it's a warm climate. There are a lot of mobile homes. So for relatively weak tornadoes, they tend to do a lot of damage. So it's a significant forecast problem.
Yeah, thank you, Stan. How much is this of an issue in other regions? Like, for example, Southeast Asia, do they have similar, like these typhoons? Do they also produce tornadoes? And
Yeah, I have not done, I've not really looked at their global distribution, but I don't see why they wouldn't. Yeah. I mean, I think it's a pretty generic aspect of landfalling tropical disturbances. I think in Asia it's more complicated because there's terrain right along the coast, where they make landfall. So you tend to hear more about extreme rains, which of course occur with landfalling U.S. tropical cyclones. But
Yeah, I already know the answer to this question because you answered it for me, but maybe the others would be interested. Why is the significant tornado parameter not very good here?
because there don't tend to be too many tornadoes that are stronger than EF2, which is what it's based on. We actually looked at that. Dave made plots of that, and a reviewer in the paper asked us that question. But it was hard to establish statistical significance there because there just weren't that many. Even in this 27-year database, there weren't a huge amount of tornadoes that were EF2 or greater. The relative percentage of them were probably less than 5%, maybe even more like 1 or 2%.
Okay, thanks again, Stan, and please join us for cookies and refreshments.
I will. Thanks.